Hey guys, this is going to be a video over chapter 14 for dual credit chemistry, acids and bases part 1. Alright, so before we get into it, we need to just talk about what acids are. Acids have the following properties. They taste sour, they dissolve metals, some of them. Acids turn blue litmus paper red. So that's what this is right here. It's a picture of blue litmus paper. It's kind of like a light purple really. And when you stick it in an acid, it turns pinkish in color. Acids all start with H, at least for you guys. There are some ways where organic chemists and stuff will not start the acid with the H, but the H is the acid part, and that's what we're going to talk about in this chapter. So when I look here at hydrochloric acid, over here, it starts with H. Nitric acid, it starts with H. Acetic acid also starts with H, and sulfuric acid actually has 2 acidic hydrogens. Acids, a big group of acids is called carboxylic acid, and carboxylic acids have this group Cu. And like I said, some organic chemists will write it like that at the end. So this H is that acidic hydrogen that gets lost, what we're going to talk about here in just a little while. So acetic acid is one of the smallest carboxylic acids. And then we have malic acid and citric acid, which you're all familiar with from oranges and lemons and stuff. All right, bases. Bases have a bitter taste, bases have a slippery feel, and bases turn red litmus paper blue. So over here, the red isn't really red, it's more like a pink color, and it turns it a very light blue or purplish color when it's put into a base. And caffeine is an example of a base. That's why coffee actually tastes bitter, because coffee itself is actually acidic. So sodium hydroxide and potassium hydroxides are bases. I put some information here if you want to pause it and read it about how some bases work, but it's really, I'm not going to be testing you over that content. All right, so definition of acids and bases. First, we're going to talk about the Arrhenius definition. Now, this definition is expanded later, and that's why it's defined as the Arrhenius definition. But the Arrhenius definition of acids is something that produces H+ ions in an aqueous solution. Now, before we get any further, I want to define what H+ is, because you'll probably hear me use the term proton, and I want you to understand that H+ and a proton is the exact same thing. So if we have hydrogen, hydrogen has 1 proton and 1 electron. Now, if it becomes H+, then that means it's lost this electron. So essentially, hydrogen is just a proton, because hydrogen doesn't have any neutrons or anything else. So H+ is just a proton. And that's all it is. All right, so HCl is a covalent compound. It does not contain ions. But in water, HCl ionizes to form H+ and chloride ions. So when we put the HCl over here on the right side, if we put HCl into water, it separates into its ions. And that's how we define what an acid is, according to the Arrhenius definition, is something that produces hydrogen ions in water, in an aqueous solution. Hydrogen ions are really reactive, and so what they do in water is they bond to the water and they form something called hydronium. It's written right here because that's terrible handwriting, I know. And so all the hydrogen ions always associate with water molecules, and so these two things are used interchangeably. So wherever you see hydronium, it is equivalent to H+. So depending on how the question is written, it could say H3O+ or H+. They both mean the same thing. All right, in the molecular formula for an acid, we often write the ionizable hydrogen first. So ionizable hydrogen means the proton that gets released as an acid. So if we look here at this would dissociate into H+ and then CHO2 negative. And you don't have to be able to do that technically, but I want you to realize that this first H is the one that's coming off. And so right here, this is the H that's being released. It's the one that is bonded to the oxygen, not the carbon. All right, so the Arrhenius definition of bases. Bases produce hydroxide ions in an aqueous solution. So if we put sodium hydroxide into water, since alkali metals are always soluble, then that means that this will separate into sodium ions and hydroxide ions, shown by this reaction down here at the bottom, the right. Sodium hydroxide is an Arrhenius base because it produces hydroxide ions, and it dissociates into those component ions. So, all right, molecular compounds containing a hydroxide group or an OH group, it's actually called hydroxyl group, such as methanol, does not dissociate in water because these are molecular compounds. They're not ionic. So you kind of have to watch out for that, and I usually don't try to trick you like that, but alcohols are not going to make OH negative because it's not ionically bonded, whereas this is a metal and hydroxide, right? The sodium is a metal, and with the hydroxide it's ionic, so it makes these two ions. This is not like that because it actually is a CH3 that's bonded to the hydroxyl group in a covalent bond because both of these, this is a nonmetal. Under the Arrhenius definition, so the acids, remember, make H plus in solution, and bases make OH in solution. So when you put an acid with a base, the H plus and the OH makes water, and that's why acids and bases neutralize each other and why we call an acid-base reaction a neutralization reaction. All right, so this is the real definition of acids and bases that's used more today, because what they found was some of the things that should have been defined as acids and bases, in fact, were not under the Arrhenius definition. So this makes it a broader category. An acid is a proton donor, so it donates H+, and a base is a proton acceptor. So acids give off the H, and bases accept the H. So according to this definition, HCl is still a Bronsted-Lowry acid. If we have HCl and we put it in water, the HCl dissociates completely, like we talked about before, and the H's attach to water, and the chloride is left behind. So this loses the H to the water, and we get hydronium and chloride. And so that definition clearly shows what happens to the proton and how it associates with a water molecule to form hydronium. The Bronsted-Lowry definition works well with bases like NH3 that don't have the hydroxide ions directly on them, like sodium hydroxide or potassium hydroxide. These, you can see the hydroxide. You can't see the hydroxide with ammonia, because when you put that in water, what happens is ammonia is a base because it will take an H from the water, leaving hydroxyl behind. So if you have water and you take the H away from it, we end up with an OH left behind, and that's how it is a base. So this now is a good definition for compounds that would previously not maybe been classified as a base, but still behave like a base in water, because it does produce hydroxides, just not in the direct way. Okay, so some substances like water can act as acids or bases, accepting or donating a proton. And we call those amphoteric. So amph, this, like an amphibian can live on land or in water, amphoteric can act as both an acid or a base. So this is the reverse reaction of the second reaction on the previous slide. And you can see here, if we go forward in this reaction, this going forward would be losing its hydrogen to the hydroxide, because here it's NH4 and over here it's NH3. So that means it's lost its hydrogen to hydroxide. So really going forward in this is incorrect unless they're talking about the reverse reaction. It is an acid because it's losing hydrogen, and acids lose protons and bases accept protons. So this is the base. And going in reverse, let me change the color here. Going in reverse, we see that water loses its hydrogen to NH3 because NH3 on the left side of the reaction has an extra hydrogen. So that means that this went to here, and so this is the acid and this is the base going in reverse. So here, yeah, it says NH4 is the proton donor, the acid, and OH is the proton acceptor, the base. And so what we see here is that NH3 and NH4 are called conjugate acid-base pairs because they're related to each other by one hydrogen ion, by one proton. So a conjugate acid-base pair is defined as any two substances related to each other by the transfer of a proton. So we have NH3 and NH4 and H2O and OH. So this is the acid here on water. Water's the acid because it becomes OH after we've lost a hydrogen. So, and then going in reverse, this would have to take a hydrogen in order to become water. So if something takes a hydrogen, that's defined as a base. So it's a conjugate base of this acid. And up here on NH3 and NH4, if we go in this direction, this has to lose a hydrogen in order to become this one, and this one has to gain a hydrogen. So anything that gains a hydrogen is a base, and anything that loses a hydrogen is an acid. And if they're related to each other by one H plus, then they're conjugate acid-base pairs, but it can only be one H plus. So if we look at this reaction, we have H2SO4 put in water. If you didn't know what was acid and what was base here, you would look on the product side and say, okay, what happened? Well, I immediately noticed that my acid lost a hydrogen, so this lost H plus, so it would be defined as the acid, while H2O gained H plus, so it would be defined as the base. Now looking in reverse, this right here is going to gain H plus in order to get from here to here. So it has to be a base, and it's the conjugate base of this acid because they're related to each other by the transfer of one H. And then here, this is the conjugate acid of this base. So in an acid-base reaction, a base accepts a proton and becomes a conjugate acid, and an acid donates a proton and becomes a conjugate base. So after the loss of the H plus, it becomes a conjugate base, and here the base, after it gains the H plus, it becomes the conjugate acid. So what is the conjugate base of the following acids? So I know acids lose H plus. So if this loses this H plus, then I would have NO2 left. And if I add these two back together the way that I have it written, then I would end up with HNO2 plus. So we have to make sure that this plus cancels out. So this is going to have a negative charge. So this would be my conjugate base here. And this one, I have to remove one of the H's, only one, because they have to be related to each other by one H. Then this would be H plus and HSO3 negative. So this would still have a hydrogen here. So it could either continue to act as an acid and lose this hydrogen, or it could gain this hydrogen from something and act as a base. This is amphoteric, this one. It didn't ask us about that, but I thought I'd throw that in there. All right, what is the conjugate acid of the following? So here we have water, and if we're wanting to find the conjugate acid, that means that these are acting like bases. And so bases gain hydrogen. So we're going to add an H plus to all of these. So if this gains a hydrogen ion, then it becomes hydronium. And if this one gains a hydrogen ion, then it becomes H2SO4. All right, so I'm going to make up a reaction here. Let's say we've got
NH3 plus
Okay, we have NH3 plus HSO3 negative goes to NH4 positive and sulfite. And we want to know which one's the acid, the base, the conjugate acid, and the conjugate base. So I'm first going to look at this, and I'm going to see what happened to it. Well, NH3 gained a hydrogen and became NH4 positive. So if it gained a hydrogen, then that means, by definition, this is the base. And after bases gain a hydrogen, they become conjugate acids. Okay, and then right here, we have HSO3 negative, and it becomes SO3 2 negative. So that means this lost H plus. So it is going to be the acid because acids lose H plus, and this will be its conjugate base. So I hope that clears everything up. And if you have any questions, please make sure you write them down or email them to me, and I'll be happy to help in any way that I can.